Hello. In this video, we will go through chapter 9 in the Earth Science textbook, which is all about running water and groundwater. So in this chapter, we're going to take a look at the water that is found on the Earth's surface and also below the Earth's surface, and how this water is able to shape and provide features to the Earth's surface. So first we have to think about the water cycle, or the hydrologic cycle. So the Earth essentially has a finite amount of water. And this water is constantly moving between the Earth's spheres. We looked at the Earth's spheres back in chapter 1, but that's the hydrosphere, the atmosphere, the geosphere, and the biosphere. So the water that's found on the surface of the Earth and below the surface is a constant amount. We maintain this overall water balance. However, it's constantly moving between those different spheres in what we call the hydrologic cycle, or the water cycle. And there's a lot of different processes that are involved in this water cycle. So now we're going to watch the smart figure video that goes along with this, so you can see where water is found on and below Earth's surface, and also how the water is cycled, these different spheres through the different processes.
Hello there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the basic functioning of the water cycle
and describe what proportion of the world's water is found in rivers. Here's an example of a river. It's flowing through a relatively arid region of the world. Rivers like this are the lifeblood of communities that live in these dry parts of the world, and they're also the most important agent for sculpting the landscape. But river water is actually a very small percentage of the total water in the world. Most of the water in the world is found in the oceans, about 96.5% of all the water. A small additional component is found in saline lakes and saline groundwater. And of all the water in the world, only about 2.5% is fresh water. Now we want to zoom in on that 2.5% and examine it closer up. Of the 2.5% of the world's water that is freshwater, about 68% of that is present in glaciers or ice sheets. Of the part that's not frozen, we see groundwater, and then there's about 1.3% of the total that is surface water and other fresh water. And once again, we want to zoom in on that water and take a look at what it is. And you can see that actually, even though it's not part of glacial ice, there's still snow and ice is a large part of that, around 73%. Around 20% is in lakes. All right, so even though lakes are really prominent on our maps, they're only 20% of 1.3% of 2.5%. Of the part that's not snow and ice and the part that's not lakes, we've got soil moisture, swamp water, the water that's in our atmosphere, the water that's in living organisms, and then the only thing left, the remaining paltry 0.46%, is present in rivers. So rivers are a tiny proportion of a tiny proportion of a tiny proportion of the world's water, yet they are quite important. Rivers are part of the water cycle. The water cycle is driven by heat energy that's provided by the sun, and that sun energy warms up water that evaporates. It evaporates and enters the air. As it is in the air, it can end up settling out again in the form of precipitation. This is either rain or sleet or snow. And as it falls down onto the land, basically that water has three options. Option number one is that it can evaporate again and go back into the clouds. Option number two is it can soak into the soil and go underground, and we call that infiltration. And option number three is it doesn't re-evaporate, it doesn't soak into the ground, and instead it simply runs off over the surface of the earth. And that, of course, would be the water that ends up in rivers. Okay, is this an example of evaporation, infiltration, or runoff? Well, hopefully you identified this as a cave, and you know that caves are underground. Caves are carved by groundwater, and so the water would have had to have infiltrated in order to produce this cave, not run off or re-evaporated. Good job. Thanks very much for your attention. This has been another Smart Figure.
So as you saw in the video that you watched, there are a lot of processes at work that keep this water cycling throughout the environment. So now let's take a look at running water. So as you saw from the video, when precipitation falls to Earth, it either infiltrates, so gets down into the soil to become part of our groundwater, or it moves down slope as runoff. So what causes runoff? Well, we have to look at how much rain and how long is it raining. At some point, the ground becomes saturated. And if no more water can become infiltrated because it's raining too hard for too long, then that water is going to start to run off. What is the nature of the surface material? So what's on the surface? Is there a lot of vegetation that could take in more water? Or is it sandy? Is it rocky? Is it an urban area? Urban areas tend to have a lot more runoff because of all the pavement, all of the concrete, the buildings that are found there. What is the slope? Are we talking about a relatively flat area, or are we talking about a mountainous area? Of course, water going down a slope is going to go faster, and there's going to be more runoff because of gravity. It's not going to be able to soak in as much. And then, like I mentioned with the surface material, what's vegetation is there and how much? Is it a bare area, or is there a lot of vegetation? So let's look a little bit closer at these drainage basins. So when we look at a drainage basin, we can divide it into three parts: the zone of sediment production, the zone of sediment transport, and the zone of sediment deposition. So in the top zone, the zone of sediment production, this is located in the headwater region. This is where most of the sediment is derived. It typically starts as bedrock that is broken down by weathering and then transported down slope. Bank erosion, so erosion that's occurring along the banks of these streams and tributaries and the main river channel can also provide sediment. And the scouring of the channel bed also provides sediment as it deepens the channel. So then the middle area here is referred to as the zone of sediment transport. And this is basically how all of this sediment is being transported. These are called trunk streams. When the trunk streams are in balance, the amount of sediment eroded from their banks equals the amount that is being deposited elsewhere. So that's why we refer to this middle portion as a zone of transportation, because we're not getting more sediment produced or more sediment deposited. This is just a main location for sediment transport. And then finally, we get to the zone of deposition, and this occurs once the river reaches the ocean or another large body of water like a lake. It slows down as it reaches that, and the energy that is being used to transport all of this sediment is reduced. So the sediment is going to accumulate at the mouth of the river to form a delta, which we'll learn about here in just a minute, or it can be moved by wave action to form coastal features like bays and estuaries or sandbars, or it can get into the ocean currents and be moved way offshore. It is primarily going to be the fine sediment that reaches this zone of deposition. So that's going to be like clay and silt and some of the finer sand grains that reach there. Now, when we look at stream networks, they are going to form distinctive patterns based on the terrain that is present. And there are 4 different drainage patterns that we can see that are the most common. So the first one there is a dendritic pattern, and this is what is the most common form of drainage that we see. It resembles like the branches on a tree, and that's where its name comes from. Dendritic means pertaining to trees or branches, and that's what it looks like. This type of drainage pattern is going to develop where the underlying material is relatively uniform, and it's going to be determined by the slope of the land and the direction of that slope. When streams diverge from a central area, like we see here with this volcano, we can get what is called a radial pattern. And this is like spokes of the hub of, or from the hub of a wheel. A rectangular pattern exhibits right angle bends, and this develops on bedrock that is crisscrossed by joints or faults. The joints and faults are going to be eroded more easily, and so that is the pattern that the stream tends to take. And then we can have a trellis pattern, which kind of resembles the dendritic pattern, but it is more of a rectangular shape, and the tributaries are nearly parallel to one another. And this is where we find this in areas where we have alternating bands of resistant bedrock and weaker bedrock. So stream flow is how the water moves, how fast it moves, and then what changes we can see from upstream to downstream. So to discuss the stream flow characteristics and the next section, which is the work of running water, and also the next section, which are stream channels, we're going to watch a little bit longer video, a mobile field trip, where we take a look at the Mississippi River and all of these pieces as it applies to the Mississippi River.
Hello, I'm Michael Collier. On this field trip, we'll be flying over parts of the Mississippi River to see how the largest river in the United States flows from its source to the sea. 75 million people live and work in the 31 states and 2 Canadian provinces that make up the river's drainage basin. They all need water from the river to live here, and at the same time they all use the river to dispose of household, industrial, and agricultural wastes. On our way downstream, we'll try to understand how the Mississippi grows and flows, how it creates landscapes in its floodplain, and how people have come to live and work alongside it. The Mississippi's official source, or headwaters, is Lake Itasca, 1,475 feet above sea level in northern Minnesota. Let's travel downstream, 2,340 miles to its mouth where the river empties into the Gulf of Mexico. This is more than just one river. Tributaries add water from the whole basin, more than 1 million square miles stretching from the Rocky Mountains to the Appalachians. That's 41% of the contiguous United States. Only the Congo and Amazon river basins are larger. One major tributary, the Missouri River, is actually twice as long as the upper Mississippi above their confluence. Another, the Ohio River, delivers a lot more water to the main stem channel than the upper Mississippi. Go figure. But rather than debating about which branch is the longest or carries the most water, We can think instead about an entire basin with multiple tributaries, the Missouri, Ohio, the upper Mississippi, all coming together to form the main trunk of the single mighty river. The Mississippi River is dynamic. It's always changing. Did you know that its current flows faster along the outside of a bend than on the inside? Because of this difference, water erodes the outside of a bend to form features called cut banks. Water on the inside moves slower and tends to drop its load of sand to form point bars. In this way, the river continuously creates loops called meanders. But when the next flood rolls through, the Mississippi might cut through one of these loops, shortening its course and steepening its gradient. By this process, oxbow lakes can form when a meander is totally cut off. The river could change course overnight, or it might take many years to change. Time enough for a town in, say, Tennessee to wake up one morning and find itself in what suddenly become Arkansas. A river's drainage basin is defined by its wettest tributary, the longest stretch of a river from headwaters to mouth, the total area from which a river's water flows. The drainage basin is the total area from which a river's water flows. At its mouth, the flow or discharge of the Mississippi averages just under 600,000 cubic feet per second, or CFS, by that measure making it the 8th largest river in the world. The river's discharge is hardly constant, though. Floods radically change the river's personality. High flow events on the Mississippi are not brief flash floods, but rather regional floods that build and subside over many days or even weeks. In 1927, high water forced almost 1 million people from their homes, not quite 1% of the United States' total population at the time. During the flood of 1993, 75 communities were underwater as 1 million CFS rushed past St. Louis. Further downstream in 2011, more than 2 million CFS swept past Vicksburg, Mississippi. Discharge is one measure of the river, but there's also the flow velocity or speed of the current. You might think velocity would be controlled primarily by the river's gradient, that is, by how much the bed drops over a given length of channel. But you'd be wrong. Gradient matters, but discharge matters more in determining the Mississippi's flow velocity. The basin's tributaries, for example, plummet thousands of feet as they first leave the high Rockies and the rugged Appalachians. But by the time it passes Mark Twain's home in Hannibal, Missouri, the main stem Mississippi has less than 500 feet left to fall before reaching the Gulf, 1,260 miles downstream. Even though the gradient of the remaining riverbed is low, the river flows faster here than in its upper stretches, and at flood stage the lower Mississippi can accelerate to 8 or 9 miles an hour. With increasing velocity comes turbulence and a dramatic increase in the river's ability to erode its banks and bed. There is also a greater ability to carry sediment downstream, either suspended in the rushing water or rolling and bouncing along the bottom as bedload. In 1927, floodwaters inundated 27,000 square miles along both sides of the river from southeast Missouri all the way to the Gulf, submerging some communities and fields under 30 feet of water. Of course, floods like this are catastrophic, but they're part of the river's natural behavior. Before the advent of artificial levees, floods would build natural levees as sand grains settle out just beyond the river's normal banks. Beyond these levees, high water would often cover the Mississippi's floodplain that stretched up to 70 miles beyond the river's edge. This level, fertile floodplain has been plowed into farmland that now helps to feed much of our nation and the world. A greater load of sediment, however, has always been carried on downstream to the river's mouth. As the Mississippi approaches sea level at the Gulf of Mexico, it slows down, breaks into channels called distributaries, and begins to drop its prodigious sediment load, something like 230 million tons a year. The result is a massive delta. The building blocks of the delta are a mix of small and larger particles. Coarser grains tend to drop out early as the river slows. Some fine particles are deposited on the delta, but most remain in suspension and travel well out into the Gulf. For the past 6,000 years, ever since sea level rose and stabilized after the Quaternary Ice Age ended, the Mississippi River has been building up its modern delta, first one lobe, then another, as accumulating sediments repeatedly divert the river's flow. So far, the river has created 7 of these deltaic lobes. Someday it will jump from its current channel and flow down the Atchafalaya River in a shorter, steeper route to create yet another lobe. If the river succeeds in switching to a different channel, as indeed it someday must, Cities like Baton Rouge and New Orleans will no longer have river access. The U.S. Army Corps of Engineers is trying to prevent, or at least delay, this geologically inevitable event because of the staggering negative economic impact. People have moved up and down the Mississippi for hundreds, if not thousands of years. The river is famous for its iconic paddle wheel steamers, but those were displaced with the advent of diesel engines. Now towboats push 6-acre barges laden with fertilizer, grain, and coal, commerce that sustains the nation's midsection. The Mississippi is a working river. As America's most important waterway, it's been heavily manipulated. Above St. Louis, 42 locks and dams aid navigation, affect the flow, and trap the river sediment. Artificial levees have reduced the seasonally wetted floodplain area by 90%. Millions of people living along the Mississippi rely on treatment plants to make the water drinkable, even though it's been used and reused many times upstream. Fertilizers are flushed from farmers' fields and enter the river. These chemicals are carried downstream to the Gulf of Mexico, where they promote the growth of algae, which, when it dies, depletes oxygen. In this way, a 7,000 square mile hypoxic dead zone has been created off the coast of Louisiana and other Gulf states. With so much industry along the river and so much agriculture spread across its floodplain, pollution has to be managed and minimized. We ask a lot of this great river, and we've profoundly altered it in modern times, but it continues to shape the heart of this country. What did you learn? The Mississippi River's flow velocity is primarily controlled by gradient, discharge, channel roughness. Discharge controls the Mississippi River's flow velocity, or speed. If you had to choose, which one of these stretches would you say is lower in the Colorado River basin, and why? Rapids on the Colorado River show that it's quickly losing elevation as it tumbles through Cataract Canyon in eastern Utah. By contrast, the river has a much lower gradient as it flows peacefully through the Imperial Wildlife Refuge on the western border of Arizona. Lower gradient can suggest that a river's mouth is close by.
So that was a pretty interesting look at the Mississippi River that discussed some of the principles and properties of stream flow. So now we're going to look at shaping stream valleys. So the stream valley is the channel and all of the surrounding terrain that directs water into the stream. And so we have the valley floor, which is the lower flatter area that is either partially or totally occupied by the actual stream channel. And then we have the valley walls that rise above the valley floor. Now we can have two different types of stream valleys. We can have broad valleys and V-shaped valleys. Alluvial channels often flow in valleys that have wide valley floors, and bedrock channels, on the other hand, will have the V-shaped valleys. In some arid regions, so out west, like in Utah and Arizona, the weathering is very slow, and a lot of that bedrock is resistant to weathering. And so these very narrow valleys that have almost vertical walls are formed, and those are called slot canyons. And there are quite a few in and around Zion National Park, and then the Grand Staircase, Escalante Natural Area. There are a lot of different slot canyons in those areas. So the base level is the lowest point that a stream can erode to. So as a stream goes through its channel, it can't just endlessly erode the channel deeper and deeper and deeper. There is a limit, and that's called base level. Base level is the lowest elevation that a stream can erode its channel, and this is the level where the mouth either encounters the ocean, lake, or another stream, and that's considered the ultimate base level. Temporary or local base levels include lakes or resistant layers of rock, and And then main streams are going to act as the base level for their tributaries. So here's kind of an example of the base level. So we've got a stream kind of going downstream here. We've got a delta as it fans out. And so the ultimate base level is going to be sea level. But if we were to build a dam, the stream profile is going to change because now we have deposition and that base level has actually gone up a little bit higher. So we can alter the base level of a stream. And when we look at how we shape stream valleys, so valleys can become deeper. These would include our V-shaped valleys. And in a V-shaped valley, the walls are very steep. We get down cutting. And this occurs because the water is moving faster. And so there is more erosion that's taking place. There's abrasion that's taking place. And so the Yellowstone River is an example of where we have a V-shaped valley. And this shows two classic features that we see in a V-shaped valley, and that's rapids and waterfalls. So you can see here in the background, we have the waterfall back here, Yellowstone Falls. And then another feature that we get are rapids. And as you saw in the Mississippi River video, this shows us that we are getting a steeper slope and that we're further away from the delta or the end of that particular stream. So what happens is that we get this V-shaped valley that's caused by the tremendous power and energy of the water flowing through. Now, when we look at more of an alluvial channel, the valley tends to become wider and not steeper. And so this occurs when the stream has cut its channel closer to the base level and we don't see as much downward erosion. The channel can take on this meandering pattern. So the energy is more side to side. And so the valley is going to get wider and wider as the river cuts away one bank and then cuts away another. So here's an example of the development of a floodplain, which we see in valley widening. So we've got a narrower valley, and so the river starts to kind of meander, kind of go back and forth from side to side, and erosion is going to take place both on the outside, or more on the outside edge, as you saw in the Mississippi River video. And instead of the sides getting more narrow, the base just gets wider. And so we get this wider and wider area. We can get more meanders or more, curves and bends. We can get these oxbow lakes that inform that where the flow gets cut off from the original stream channel. Changing the base level we can create these incised meanders. An incised meander occurs when we have an area where there is uplift that occurs. The meanders probably first developed on the floodplain of a stream that was in balance with this base level, like I just showed you. But then there was a change in the base level for whatever reason, and the stream started to downcut. It started to carve out those more V-shaped or more steep walls. And this is either caused by a drop in the baseline or the uplift of land. And so we see a lot of these incised meanders out west, particularly around the Colorado Plateau. So in areas of Colorado, Utah, New Mexico, Arizona, in that area, where there was a regional uplift of that entire plateau. And so the first page of this chapter shows you a picture of an incised meander, or a couple of them, in Canyonlands National Park in Utah. So the next section gets us into depositional landforms. So what are some of the features that we can see that are caused not by erosion, but by the deposition of all of that sediment? So as you saw in the video, we have deltas where the stream channel enters a still body of water, most commonly the ocean, but it could also be lakes as well. And a delta is going to occur because those sediments start to drop out because the current is dying. And we can get different patterns, as you saw in the video. And, you know, the stream, especially something like the Mississippi River, is going to find the path of least resistance. And that's why he mentioned in the video that one of these days, the Mississippi River is actually going to start flowing to the Gulf through the Atchafalaya River. We're trying to stop that, of course, because if that happens, New Orleans would pretty much cease to exist as we know it today. Where New Orleans is where ocean was less than 5,000 years ago. And that's because of the way the Mississippi River has moved through those distributary channels. Now we can also have natural levees. So natural levees can occur as the sediments start to drop out on both sides of the bank. And behind those natural levees, we can get what are called back swamps or Yazoo territories. So as these levees build up, it blocks off the flow of tributaries to the mainstream channel. And so this can lead to marshes if the water kind of comes to a standstill, or it can lead to these Yazoo tributaries, which cause a stream to run parallel to the river. And these Yazoo tributaries are named after the Yazoo River in Mississippi, which parallels the Mississippi River for almost 200 miles before it finds a way back to join it. And then we can have alluvial fans. Alluvial fans typically develop where we have a drop in velocity from a mountain stream to the base of a mountain. We'll study these a little bit more in the next chapter. These often occur in more arid regions, in the deserts, where we have areas where we have a rainy, or times when we have a rainy period, and then it becomes very dry. And so the water doesn't flow across this alluvial fan. And so these streams grow intermittently. So we'll focus on those a little bit more in the next chapter. So looking at floods. So when the stream overflows its channel, that is called a flood. And they are the most common and most destructive of all of our geologic hazards. But they are part of the natural behavior of streams. So what causes floods? Well, rivers flood because of the weather. Okay. Rapid melting of snow or storms that come through bring heavy rains that causes a regional flood. You saw a little bit about this in the video, that we have had multiple regional floods throughout the Mississippi river, throughout time. Down in Louisiana, in Mississippi, Arkansas, Tennessee, Missouri, all of these areas have been subject to these regional floods. Flash floods occur with little warning, potentially deadly, because the water rises so rapidly. This is due to rainfall intensity and duration, the surface conditions, and the topography. We are seeing this play out right now in western North Carolina and eastern Tennessee due to Hurricane Helene. In some of the areas in Appalachia, in that particular region, they saw 20 to 30 inches of rain in a very short period of time in areas that were already saturated. So this increased runoff. You also have mountainous topography, which increases runoff. A lot of these valleys that have streams were not V-shaped valleys, so they could not hold the amount of water. They were flatter, they had floodplains, and the water just overwhelmed those areas because it was so much water in such a little amount of time. We also, as humans, interfere with the stream system. We can build dams, we can build levees, and when those collapse, and we're also kind of seeing a little bit of that in western North Carolina as well, when those collapse, all of that water behind those that was being held back now rushes into an area. So how do we help with this? How do we help control floods? Well, we can use artificial levees, we can use, or we could build dams, and we can help to affect the river channel. So artificial levees are built on the banks of rivers to control them, to provide a geological barrier. It increases the amount of water that the channel can hold. These are distinguished from natural levees because of the steepness. We build dams to control floodwater, and then we allow so much to be released. So in times of, drought, we can lessen the amount that flows through the dam. When we have a lot of rainfall, we can open the dam and try to let more water out. This affects us here in this region because we have the DeQueen Dam, we have the Gillum Dam, we have the Broken Bow Dam. So we have several dams around here that are used for flood control, and the amount of water that's let out is determined by weather conditions and rainfall. Of course, dams can also be used for hydroelectric power and providing water for irrigation efforts. However, building dams is expensive, and it can have other consequences. Reservoirs created by dams can cover up forests, they can cover up farmland, historic sites, and all of that. Then we can have what is called channelization, which is when we alter the stream channel. This can speed up the flow of water and prevent it from reaching flood height. And so one of the common ways that this is done is through river dredging. And basically what dredging does is it tries to pick up the sediments and kind of move them out of the way so that the bed is deeper, a little bit wider, allows the flow of more water. The Corps of Engineers does a lot of this. They're responsible for building a lot of the dams that we have around here and dredging the river. But now we are more into non-structural approaches through floodplain management. Basically identifying high risk areas and then zoning those, and having regulations on the zoning so that we minimize the number of people and houses and businesses that are in these potential floodplains. So now we'll focus on groundwater. So looking at water below the surface. Many people believe that groundwater occurs in underground rivers, which is really just not true. It is the largest freshwater reservoir for humans, and groundwater, just like surface water, can be erosional. So groundwater, of course, is super important. You can see that in terms of our liquid freshwater, 96% of it is going to be groundwater. Wells and springs provide water for cities, crops, livestock industry, and groundwater is the source of about 40% of the water used for all purposes. However, just like with everything else, we have overused groundwater, and that can present problems. So when rain falls, we've already talked about some of that water is going to run off, some goes back to the atmosphere, and then the rest of it is going to infiltrate. Now, the amount of water that infiltrates varies from time to time and place to place. And this is determined by the steepness of the slope, the nature of the surface material, the intensity of the rainfall, and the type and amount of vegetation. So when we look at the distribution of groundwater, some of the water that soaks in is held right there in the soil, and that is called the belt of soil moisture. It's very close to the surface. This is where we find, tree roots, burrows of animals and worms, and all of these things can influence the amount of water that is infiltrated. Water that is not held in that belt of soil moisture keeps going downward until it reaches a zone where all of the pore spaces in the material are filled with water. And that is our zone of saturation. And this is where the term groundwater comes from. The upper limit of this is called the water table. The area above the water table, where the soil and sediment is not saturated, is called the unsaturated zone. So the water table is not typically level as we think about with a table. As you can see in this figure here, it is a replica of the Earth's surface, where we have the highest elevations beneath hills and then a decrease in elevation toward the valleys. The water table of a wetland is usually right at the surface. So what you're seeing in a swamp or in that type of area would sometimes be partly groundwater. Lakes and streams occupy areas low enough that the water table is above the land surface, which is what we're seeing right here in this valley. So the nature of the materials that are beneath the surface influence the rate of groundwater movement. And so these two factors are the most important. This is porosity and permeability. So water is able to soak into the ground because bedrock, sediment, and soil contain openings or pores or pore spaces. And so the quantity of groundwater that can be stored depends on the porosity of the material. And porosity is the percentage of the total volume of rock or sediment that consists of pore spaces. And so this is a demonstration of porosity. So we have several beakers here, and we've got 1,000 milliliters of sediment here, and then 1,000 milliliters of water. And so now we have poured in 500 milliliters of water. So we've been able to take something that was seemingly full and now add water to it, so that water is able to get in between all of these spaces. And so the porosity is 50% in this example. So the pore space depends on the size and shape of the grains, how tightly they're packed together, and in sedimentary rocks, the degree of cementing that has occurred. Now, permeability is the ability to transmit a fluid. Now, the movement of groundwater is pretty slow, just a few centimeters per day. So it takes time for that infiltration process to occur. So looking at wells, artesian systems, and springs. So wells are the most common method for removing groundwater. There are approximately 16 million water wells in the United States. More than 13 million of those are private wells. To ensure the continuous supply of water, a well must go below the water table. But when a substantial amount of water has been withdrawn, the water table around the well is lowered, and this can cause what we refer to as drawdown and can form a cone of depression in the water table, like we see here. So we've got a well here, looks like maybe to be for personal use. We've got a well over here for farm use, and now we're drilling a new high capacity well. So a lot of pumping has occurred at this high capacity well that was built here, and this has caused a cone of depression. Because this well is so deep, it still has water that flows out of it. But now these two wells, which once were down into the water table, are no longer in the water table, and so they've gone dry. So the only way to fix that would be to drill this well deeper or stop the high rate of pumping that's coming out of this high capacity well and allow the water table to, start to fill in here and then eventually get a little bit higher like it was. And we can also have artesian systems, and we're going to watch another smart figure video that goes through
Hello, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe what an artesian system is and distinguish between flowing and non-flowing artesian wells. This is an example of a flowing artesian well.
Basically, all you have to do is drill a hole in the ground, and then coming up out of that hole, boom, is water. It kind of reminds me of the opening sequence of the Beverly Hillbillies, where Jed's out hunting rabbits, and he shoots his rifle, and the bullet pierces an aquitard, and that aquifer underneath holds not water, but oil, and it starts oozing out onto the ground. It's the same thing here, except groundwater is what's flowing out of this hole. So let's take a look at two examples of these artesian wells. We're going to take a look at one that's very close to the recharge area, and then we're going to take another look at a second one that's further away from the recharge area. So let's go ahead and take a look at the first one here. We're going to zoom in on this area. You can see here that we've got an aquifer that's confined by two aquitards, one above and one below. You can see that the top of the groundwater there is the water table. And if you extend that water table off to the right, imaginarily through the aquitard that overlies the aquifer, that is what we call a pressure surface. And if you were to drill a well down and pierce that aquitard, the water would flow up in that well to that pressure surface. So the pressure surface is above the top of the aquifer, but the pressure surface is below the ground. So as a result, this is a non-flowing artesian well. Contrast that with this situation. This is more like the example that we looked at to start with. Further away from the recharge area and at a lower elevation, The pressure surface is actually above the surface of the Earth. As a result, the water in the confined aquifer wants to flow up through that well to reach that pressure surface, but basically it's hitting empty air there, so it ends up flowing out over the landscape. Gravity is more dominant than the pressure that's driving it out. This is the same exact principle we use basically to create water pressure in our houses. You know that there are these weird water tanks that are rising over the landscape in various places like UFOs. Basically what we do is we pump water up into those water tanks, and then that creates an artificial pressure surface. Then when you open the tap in your house, say to take a shower, the water flows out of that tap because it's trying to reach this pressure surface. Of course it never gets there because we don't let it flow out in high enough volume, and there's a lot of empty space for it to fill up before it ever got that high. That's why water comes out of your shower head when you turn the knob. Here's an actual example in South Dakota. Basically, we're going to take a look at a cross section from west to east across South Dakota, and you can see the Black Hills over on the left and the flat area of the Great Plains over on the right. So what we've got here is the Dakota sandstone, and this is an example of an artesian system. And basically what I'd like you to do is imagine what the pressure surface must look like in order for this area over here to be an area of flowing artesian wells. Well, okay, you had a minute to think about it. Probably what that pressure surface looks like is something like this. So it comes out over the landscape like that. And so if you're to drill a well here, piercing through this Cretaceous shale into the underlying Dakota sandstone, the water that is entering the Dakota sandstone from over here on the flanks of the Black Hills is going to try and flow up those wells and reach that pressure surface. Hopefully you got that correct. Thanks very much for your attention. This has been another.
So there you learned a little bit about artesian systems. So the last one we're going to look at here are springs. So whenever the water table intersects the ground surface, we get a natural flow of groundwater called a spring. Springs are not confined to places where the perched water table creates a flow at the surface. We have a lot of different subsurface conditions that vary from place to place, and so if those openings fill with water, then that can lead to a spring. So a hot spring, there really isn't an accepted definition of what a hot spring is. Typically, we say that the water in a hot spring is 6 to 9 degrees Celsius warmer than the air temperature. If we use that definition, then there's over 1,000 of these hot springs. Another definition that we can use is looking at the geothermal gradient, which is the temperature that we get with increasing depth. And when the groundwater is circulating at great depths, it becomes very heated. And as it emerges quickly to the surface, we get hot springs. And we have these fairly locally to us, Hot Springs National Park, so named because of the vast number of hot springs that we see in that area. They average about 60 degrees Celsius, or around 140 degrees Fahrenheit. And that is because this particular area of Arkansas has a little bit higher geothermal activity than the surrounding areas, as you saw when you did your geothermal exercise a few chapters back. Hot springs are heated by the cooling of igneous rock. And so we see a lot more of these out west where there is a lot higher geothermal activity. So a geyser is an intermittent hot spring. So what happens is the water is so deep that it is under great pressure. And so the pressure there prevents the water from boiling at a normal temperature. So it gets superheated, essentially. And as the water heats, it expands, and then it shoots out of the ground as a geyser. And of course, one of the most famous of these is Old Faithful in Yellowstone, but there are hundreds of geysers in this area. But you know, Old Faithful is the one that gets the most attention. So what are some environmental problems related to groundwater? Well, treating groundwater as a non-renewable resource. And where this occurs, the amount of water that's available to recharge the aquifer is less than the amount being withdrawn. And, we have water shortages that occur out west because of this. We can also have land subsidence caused by groundwater withdrawal. And this is a picture from the San Joaquin Valley, where between 1925 and 1975, due to irrigation, this part of the valley subsided almost 30 feet because of the withdrawal of groundwater. So we can see cases of this in Las Vegas, New Orleans, Baton Rouge, Arizona, and then around Houston and Galveston. And then we also have to worry about groundwater contamination. The pollution of groundwater, of course, is a serious matter. And, groundwater in some respects is self-filtering. As the water infiltrates, as it goes through the layers of, the soil and roots, and then gets into the sand and the rock, a lot of that pollution can be pulled out. But you often don't know that the water is polluted for a time, and you don't know exactly how much is going to be filtered out before it is released. And so in this example, we have, contaminated water from a septic tank that's leaking. This goes through the limestone, gets down into the water table. This happens very quickly. And so now this well is contaminated. However, in an area where the bedrock or the underlying rock is sandstone, it takes a lot longer for that process to occur because water travels through the limestone faster. And so by the time it gets to this well, it has now been cleaned by the process of infiltration. So looking at some of the erosional features that we can see with groundwater, we can get caverns and what we call karst topography. So groundwater is typically acidic because it contains dissolved carbon dioxide, which when it reacts with water forms carbonic acid. And as we have seen, we know that acid can dissolve limestone. So limestone is found all across the earth and other soluble rocks as well. And as this mildly acidic water passes through, it can dissolve the limestone. So we can have caverns. In the United States, about 17,000 caves have been discovered. Most of them are small, but we do have 2 national parks consisting of caves. We have in Kentucky, Mammoth Cave National Park, and in New Mexico, we have Carlsbad Caverns. Carlsbad Caverns are typically defined as the biggest because the rooms within the cave system are very large, but the Mammoth Cave is one of the longest. We've discovered about 350 miles of caverns beneath the surface. So most caverns form at or right below the water table in the zone of saturation. The acidic groundwater is going to follow those weaknesses in the rocks, and it's going to create cavities, and eventually these enlarge to create caverns. Within caverns, we get depositional features. So caves themselves are created by erosion, but the features that we see within caves are deposition. So in this example, in picture A here, we have what's called a soda straw formation. This is a type of dripstone feature that we see where water starts to seep through, and once it reaches the air in the cave, some of that dissolved carbon dioxide that was forming that carbonic acid escapes, calcite starts to precipitate, and then it just deposits around itself as we continue moving down. And so these would be hollow, and that's why they get the term soda straw. Another feature is and this is a type of stalactite. Here are some other stalactites formed by a little bit different process where they may not be hollow inside. And then we also get these features here on the bottom called stalagmites. And stalagmites are formations that start on the floor of the cavern and start to rise up. And stalagmites are usually more massive because as this drops on the floor, it may not drop in the same spot every time. And so the stalagmites take on a little bit different appearance. So a way you can keep these straight is stalactites hang tight to the ceiling, and stalagmites might just reach up to the ceiling. And there are a lot of features that you can see, and especially in Carlsbad, we saw a lot of these when we went on the cave tour, where the stalactite and the stalagmite actually touch one another and form a column from top to bottom. So another feature that's associated with erosion of groundwater is called karst topography. And karst topography is named for the Kars region in the border between Slovenia and Italy, where we see a lot of this type of topography. And so this is going to occur in areas where we have limestone. So we see this in Kentucky, Tennessee, Alabama, Indiana, and Florida. So what are some features associated with karst topography? We have sinkholes. Sinkholes are surface depressions. Some of them are just 3 to 6 feet to a maximum of more than 160 feet wide. Sinkholes can form in one of two ways. Some are gradual over time without any physical disturbance to the rock. And so what happens is that the limestone that's just right below the surface, right below the soil, is going to be dissolved by rainwater that contains carbon dioxide, which creates the carbonic acid. They're not very deep and they have gentle slopes. However, we can also have sudden sinkholes that form due to the collapse of a cavern under its own weight. So we're getting a cavern that's forming under the surface, and all of a sudden the rock on top of it collapses down into that cavern because there's been so much erosion that's occurred, it can't support its own weight. And so there's a figure in your book that shows this on page 299. So that brings us to the end of chapter 9 about the about water and the depositional and erosional features that we can have associated